Okay, design beam B5 and B4 as T-beam and compare the results with that of rectangular beam section. T-beams usually give an economical design as compared to the rectangular sections. But in case of simply supported beam, you can get a T-beam action for the whole beam. But in case of continuous beam, the T-beam action will only occur where there is sagging. Okay, so we'll see over here. This is our beam B5 and B4. Okay, so we can see over here there is a hogging moment. Over here in this region there is a hogging moment. Over in this region there is a hogging moment. Okay, so the section over here is shown over here. Okay, in case of hogging moment, tension is at top, that's above the neutral axis, and in case of sagging moment, compression is at top, that is above the neutral axis, and again here this is hogging moment, so tension is at top. And now we do not consider concrete in tension zone. Okay, so in this region, the flange, okay, flange of this T beam will be under tension. Okay, so the concrete in the flange will be neglected, and here you will have to design the beam as a rectangular beam. Okay, you will not get the advantage of this T action in this region where there is hogging moment, where tension is at top. You will get only advantage of T action in this shaded portion where there is sagging. Okay, so if it is a simply supported beam, then obviously you will get a very economical section when you consider it as a T beam, because in a simply supported beam there are no hogging moments, there is only sagging moment, right? So in that case you can get a very economical depth of the beam and also economical steel. But over here the depth will be governed by this moment. Okay, so because this is hogging, so T action is not preferable over here. T action cannot be allowed over here, but the depth of the beam will be governed by this moment. Okay, so even though if you want to reduce the depth because of providing T beam action, then also you cannot reduce because that depth is required over here, right? So you can only do economy in the bottom still. So we will see that how can we do the economy, or how much economical this T section can be. For a T beam action to occur, the flange has to be under compression when the moment is sagging, whereas under hogging moment the flange will be under tension, and as the concrete is neglected in tension zone, flange beam action will not come in a flange beam will not come in action, and the section has to be designed as rectangular section, which I just explained. Okay, now the procedure for analyzing flange beam at ultimate load depends upon whether the neutral axis is located in flange region or the web region. So finding of neutral axis in case of T beam is a trial and error method. So let me explain what does this mean. Okay, we can have three cases in case of T beam. First case, when the neutral axis falls in the flange, then this is a simple case, and it represents a case of rectangular section because the concrete below the neutral axis is neglected. So this you can design it as a rectangular section with width equal to BF. Second case, when the neutral axis falls in the web, but the strain point 002 falls in the flange. Okay, so in that case, let me show you the 3D view. So this is a 3D view for case 1. When the neutral axis falls in the flange, you will have a complete stress diagram like this throughout the flange. Now, when your strain point 002 falls in the flange and your neutral axis falls in the web, then you have, code says you have to take an average stress diagram with maximum with the stress at top is stress at top as 0.447 FCK, and YF is something that you have to find out, right? YF is equal to 0.15 XU. XU is the depth of the neutral axis, okay, and plus 0.65 DF. DF is the depth of the flame, but this 5 should not be greater than DF, okay. So this is how you will get an stress diagram like this, average stress diagram for the flame. Let me explain you this figure. Okay, when the neutral axis falls in the web, okay, then you divide this T beam into two parts. This is flange 1, this is flange 2, and this is web, okay. So this flange and this flange will have a different stress diagram as compared to this web. That is what we are seeing in this 3D view. This is the stress diagram, that is 0.447 FCK into YF is a stress diagram for flange 1, flange 2, and this is the regular stress diagram for the web, that is for rectangular section, right? So this is how we get the stress distribution in case when the strain point 002 falls in the flange, okay. That means when this length 3/7 XU is less than DF, okay. The second case is the flange falls in the web and the strain point 002 also falls in the web, okay. That is 3/7 XU is found to be greater than DF. In that case, YF will be equal to DF. That is the only change, okay. So YF has to be equal to DF. So this is the stress diagram for flange 1, this is the stress diagram for flange 2, and this is the regular design stress diagram for the web, right? So this is how we have three cases in case of beam, okay. So this is what this means. Okay, this line tries to explain that the procedure for analyzing the flange beam and the ultimate load depends upon whether the neutral axis is located in the flange region or the web region. So we will have to assume first a depth of neutral axis and then find whether the neutral axis falls in case 1, case 2, or case 3, okay. So let's start the design. So first you have to find the effective width of the flange, clause 23.1.2 IS 456-2000. Okay, over here we can see this is 3 meters, half of that is 1.5 meters. This is 3 meters, half of that is 1.5 meters. So the width of the flange is B, that is 3 meters, right? Okay. So we have to take least of this B or BF, okay. Least of these two has to be taken as the width of flange. So BF is given as L0/6 plus BW plus 6 into DF. L0 is the distance between the zero moment in the beam. For continuous beam and frames, L0 may be assumed as 0.7 times the effective span. Our effective span is 5 meters into 0.7 divided by 6. BW is the width of the web, that is 0.23. DF is the depth of the flange, that is 0.115. We get BF is equal to 1.5 meters. Now 1.5 meters is less than B, this is 3 meters. So we will take our effective width of flange as 1.5 meters, okay. I've written over here. Now the next step is find the actual depth of the neutral axis. So we first have to find that which case is applicable to our section. So we will have to assume the depth of the neutral axis first. So let us assume that the neutral axis is in the flange, and we are assuming that our case is case 1, and then we will try to prove whether our assumption is correct or false. So assuming the depth falls in the flange, let us assume the depth of the neutral axis equal to 115 mm. We are assuming the neutral axis is at the bottom of the flange, and XU is equal to DF, we are assuming. So this is our strain diagram, this is our stress diagram, this is C, that is equal to 0.362 FCK BF into XU. Now over here B will be converted to BF. Okay, this is point for T is equal to 0.87 F into AST. Now, in most of the cases, the actual neutral axis is found to fall in flange. In that case, the beam will be designed as a rectangular section as concrete below the neutral axis in tension zone is neglected and the width of the section is taken as BF. We are assuming the depth of the neutral axis is equal to 115 mm, that is, the neutral axis is at the bottom of the flange. From equilibrium, we know C is equal to T, C is equal to T, okay. Now, effective depth in our case is 475 mm. C is equal to 0.362 FCKBF into XU. Moment of resistance is C into lever arm. C into lever arm. Lever arm is D minus 0.416 XU. Right? So we can find moment of resistance, that is equal to 533.48 kilonewton meter. Now, our design moment is 134, which is less than the moment of resistance that this section can carry when the neutral axis is at the depth of the flange. Neutral axis is at the bottom of the flange. Okay, so definitely this is your moment of resistance, but our design moment is less. So definitely the neutral axis will fall in the flange, and the assumption that our case falls in case 1 is found to be correct. Okay, so now let us find the actual depth of neutral axis. Let us find the actual depth of neutral axis. We know moment our design moment is 134.25. Okay, so again, using this formula, C into lever arm, this is C, this is lever arm, sorry, we have to find XU actual. So solving this equation, okay, we get XU actual is equal to 26.5 mm from the top. So this is 26.5 mm, that is the depth of our neutral axis XU. So this is our design stress diagram. This is C, this is T, this is lever arm, that is D minus 0.1416 XU. Now moment of resistance, that is our moment, design moment, is equal to T into lever arm, and lever arm is D minus 0.416 XU, and this T is equal to 0.87 Fi into AST. We want to find AST, so AST is equal to MUR divided by 0.87 Fi into lever arm. Okay, so we'll find AST using this formula. So calculation of steel required at the mid span. Okay, the maximum bending moment, positive bending moment is 134.265. So we get steel 802 mm square. Okay, so we will provide a number of 16 mm dia bars. So AST provided is 804 greater than 802. So okay, so this table remains the same for left hand support and right hand support as we saw in our part 1 of this video. Okay, because they have to be designed as rectangular section, so no change will be there. The change will be only in the mid span where the moment is sagging. Okay, so we are the required steel now is 802 and we will provide 804. Okay, when we designed this beam as rectangular section, we had provided steel 981.25. Okay, so when we had designed this beam as this section as rectangular section, then we had provided steel 981.25. But now we are designing this section as T beam, T section, okay, T beam section. So the steel has reduced to 802 and we are providing 804. So we can see a economy in steel about 20%, right? So this is how T beam can be are found to be economical. But if it is an simply supported beam, then T beam action will really give a very good economy, because the whole beam will be under sagging and you can get a very good economical depth and economical steel. Okay. Now shear reinforcement that is to be provided is the same as we provided in case of rectangular section in part 1. Okay, only thing just you have to remember that for shear the formula is V divided by BD, Okay, so instead of B, you have to take BW. Okay, B is the width of the rectangular beam, that is 230 in our case, and BW is the width of the web of the T beam. That is also 0.23. Okay, because we are providing BW point, that is 230 mm or 0.23 meters. So in both the case, B, you consider B or BW, our width is same, right? So the calculations will not differ. Okay, but you have to remember that you have to change the formula by replacing B to BW. Okay, check for deflection where the moment is maximum. So this is the figure given in the code. Okay, so let me first go to the detailing, right? So the whole detailing remains the same. Only thing is, instead of 225 mm bar over here and over here, we are providing 16 mm dia bar, 4 number of 16 mm dia bar. Okay, and we are continuing two 16 mm dia bars throughout, and two 16 mm dia bar are curtailed over here, and this two 16 mm dia bar are curtailed over here at a distance 0.15 L, that is 0.75 meters, 0.75 meters from the support. Okay, that is the only change. Otherwise, the stirrup spacing and everything is the same. Okay, so that is something which we have already understood in part 1, right? Now coming to the check for deflection for the maximum positive moment. Okay, so this is the figure given in the code, which gives us the reduction factor, which we have to multiply by the L by D basic ratio. Okay, so we have to take the ratio of web width to flange width. Web width is 230, flange width is 1500. So this is 0.1533. So 0.1533 falls somewhere over here, and we get a reduction factor of 0.8. Okay, this is the reduction factor that has to be multiplied by L by D basic ratio. Okay, we will see. So reduction factor is 0.8. Now AST minimum, we know we have provided 804. The PT is 0.736. So Fs is found to be 240. Okay, so we will be using this graph for Fs 240. Okay, now PT is 0.736. So PT is 0.736, so somewhere here, and this is a graph for Fs 240, and you get corresponding KT. Okay, so KT is found to be 1.1. Kc we are considering as 1. So L by D actual is L by D basic into reduction factor. This is to be multiplied by reduction factor into KT into Kc. So this is the change. Okay, we have to multiply the reduction factor with this value L by D basic. So this is found to be 22.8. Our actual L by D ratio is 5000 by 475, that is 10.526, which is less than 22.88. So it is found to be okay in deflection. Okay. Other details remain the same. Development length to be provided. Okay, development length should be, anchorage length should be at least this much provided. If it is 12 mm dia bar, then 564. 16 mm dia bar, then 752. 20 mm dia bar, then it is 940. Okay, you have to consider the bar in tension. Okay, because in case of earthquake, the stresses are reversible, so you have to take the worst case. Okay, so this is the table. We get this development length using table 65 of SP16. Okay, and for 25 mm dia bar, it is 1175. Okay. Again, this clause that is 26.5.1.3 that when your beam depth is greater than 750 mm, you have to provide phase bars, but our is 525, so we don't have to provide the phase bars. Okay, now this is how the T beam has to be designed, right? Now let us take a design of a varying depth cantilever beam. Design a cantilever beam as shown in figure below. Use M20 grade concrete, M and Fe415 steel. Take effective cover as 50 mm. Effective cover is 50 mm. Take the width of the beam equal to 230 and total factor load applied is 100 mm. Okay, right, 100 kilonewton per meter. Sorry. Now the span of the beam is cantilever beam is 1.5 meters. Okay, so we will make design tables that will make our work easy. We will take four sections, one section at support, another section at a distance 0.35 meters, another section at a distance 0.75 meters, another section at a distance 1.125 meters. All these sections are taken, distance are from the measured from the support. Okay, so let us find the moment at this section first. Use this formula, you get the moment at this section, this moment at this section, this moment at this section, this moment at this section. Now once you get the moments, okay, these moments are in kilonewton meter per kilonewton meter, right? You can find the required D, okay, that is effective depth D. So putting the value of moment over here, you find the effective depth D. So this is the depth, effective depth required at this section. This is the effective depth required at this section. This is the effective depth required at this section. This is the effective depth required at this section. Okay. Now this is the required depth. Now we will provide a depth greater than this so that the section becomes under reinforced. So 420.97 is required. We will provide 450 mm our effective depth over here. So the effective depth over here is 450 plus 50 mm. So overall depth over here is 500 mm. Okay, and we are taking this as 300 mm. Okay? So when you do interpolation, you can find the effective depth at different sections. So over here it is found to be 425, over here it is found to be 400, over here it is found to be 325. Now 425 is greater than required over here, so okay. 400 is greater than required, okay. 325 is greater than required, okay. So at all the sections we can see that our section is found to be under reinforced. Okay, provided the provided effective depth is greater than required D at every section, so the section is singly under reinforced section. Okay, so once we know that our section is singly under rectangular under reinforced section, we can use this formula for finding the AST. Simple. Now this are the distance, this are the moments. Okay, find the AST for this moment. Okay, now D over here, you have to take the corresponding D. Okay, for this you have to take this D, for this you have to take this D, for this you have to take this D, and for this you have to take this D. Okay, so you find the area of steel. So this is required area of steel, and this is the provided area steel. Over here required is 381, we are providing 942. That is 220 mm plus 116 mm plus 112 mm bar. Okay, so this steel is has to be provided up to a distance 0.375 meters. Okay, so this is the theoretical cutoff point where you can cut this steel or reduce the steel from here. Okay, but the code says you cannot cut the steel, you cannot do the curtailment at this point, but you will have to extend the steel by a distance L0. Okay, let me explain you through the figure. Okay, so this steel is 220 plus 160 and plus 112 mm. Okay, so over here the steel is 220, 116 and 112, and we are curtailing 116 mm dia bar. Okay, so that can be curtailed at a distance 375 mm plus L0. L0 has to be greater of 12 into the maximum diameter. The maximum diameter is 20. 12 into 20 is 240, or D, that is 450. You have to take greater of these two. So D is 450, that is greater. So we have to take 375 plus 450, that is equal to 825. So at a distance of 825 mm, we can curtail this 116 mm dia bar and continue 220 and 112 mm dia bar further. Okay, so this is how we do the detailing of the main steel, top steel, tensile steel. Okay, now moving further. Okay, now AST minimum is found by this formula 0.85 into BD by Fy, that is found to be 212 mm square, but we will provide 3 number of 12 mm dia bars, okay, in the compression zone, that is bottom steel. Okay, the area is 339 greater than 212, so it's okay. Okay, so we will provide 3 number of 12 mm dia bars at the bottom. This is compression zone in cantilever. Okay, so let us move forward. Now coming for the check for shear. Okay, this is very important. Clause 40.1.1, beam for of varying depth. Okay, in case of beams of varying depth, the equation shall be modified as so. Tau v has to be found by this formula, that is v, it is not v divided by pd, but it is v plus minus mu by d into tan beta divided by pd. Now over here our question is whether to use a plus sign or a negative sign. The code says the negative sign in the formula applies when the bending moment mu increases numerically in the same direction as the effective depth increase. Okay, so let's see what does it mean. Okay, we can see our depth d increases in this direction and moment also increases in the same direction. Okay, so we will have to apply the negative sign. Okay, we will have to apply a negative sign, right? Okay, so we first we will find at different sections by using this formula. This is the v at support at 0.375, at 0.75 and 0.1 and 1.125 meters from the support, right? These are the v which we found from this formula, tau v. Now tan beta, what is tan beta? Tan beta is nothing. Tan beta is this angle with this horizontal angle of this inclination with the horizontal. Okay, we know this is 500, we know this is 300, so this is 200. Okay, so 200 divided by 1500 mm is equal to tan beta. Okay, 500 minus 300, that's 200, divided by 1500, that is your tan beta. So you know everything. Now mu, okay, what mu will take for this case? Mu you have to take this, right? What d will you take? Okay, for this case d will be equal to this, right? Similarly for this case, say, okay, then mu sorry mu for this case mu to be taken is equal to this and d to be taken is equal to this, right? So please remember that. So this is how, putting the values of mu, d, b, tau, tan beta, we get nominal shear stress tau v. Okay, this is the area of steel we calculated, right? Provided steel area. From that you can get the pt by using this formula. Okay, and tau c, for this pt we can find tau c from table 19 of IS 456 2000. So this is a tau c. Tau c max from table 20 IS 456 M20 grade, this is tau c max. Okay, now tau v should be less than tau c max. If it is found to be greater than tau c max, then you will have to change your section, right? You will have to increase your depth, right? Now but in our case tau v is less than tau c max, so it's okay. Now this is tau v, then this is tau c. Okay, so we can see here tau c is less than tau v, so we will have to provide shear reinforcement for additional shear force BUS, which is given by this formula, and that is equal to 88.314. over here also tau c is greater than tau c is less than tau c, so VUS is found to be 52.63. over here tau c is greater than tau v, so VUS will not come in action. Over here tau c is greater than tau v, so VUS will not come in action. So you will have to find the spacing of stirrups for this force and this force, and over here you have to provide the minimum spacing. Okay, minimum stirrup area, the minimum stirrup requirement has to be provided in these two cases, right? Now we are providing two legged 8 mm dia stirrups. this is the formula. You know VUS, put the value of VUS over here. D, okay, please remember for this case D has to be taken equal to this, okay, right? For this case D has to be taken equal to this, okay. So this is how you have to find the spacing, right? So this is the spacing waveform that has to be provided, okay. Now this spacing has to be less than lesser of this three, okay. So this is the spacing which we will provide, okay. We will provide 175 mm up to a distance 0.375 meters from the support, right? Then 250 mm throughout the beam. But instead of this length 0.375 meters, we will provide this spacing up to 0.5 meters. Okay, let me show you in detail. Okay, so we will provide 8 mm dia stirrups about 175 mm center for a length of 500 mm, and then remaining we provide 8 mm dia stirrups about 250 mm. Okay, so this is how we design the stirrups, right? Now we come to the next important, very important point. Check for development length, okay. Development length required for 20 mm diameter in tension is 940, okay. 94 centimeters, so 940 mm, okay. So let us see in this figure. The largest diameter is 20 mm, right? So for 20 mm the anchored length required is 940 mm, okay. Just we saw, okay, there is a 90-degree band over here, right? So the effective anchorage length of this 90-degree band is can be found by formula 8 into diameter of the bar. So 8 into 20, that is 160 mm. So this is taken as 160 mm, right? Plus this is 336 plus this is 450, okay. So 336 plus 160 plus 450, this is 946, which is greater than 940, which is required, okay. Just we saw, so it's okay now, okay. So this is how we provide the anchorage length in case of cantilever beam. Now anchorage length for the compression member, okay. So we can see the table. Development required for 12 mm dia bar in compression, okay. This is the table for development length of the compression bar for 12 mm and M20 grade concrete. The development length when the bar is in compression is 45.1 centimeter, that is 451 mm. So we are providing, this is 350 plus an L of 150 mm, so this is 500 mm, which is greater than 451, so that's okay, okay, right. So this is how we provide the anchorage length in the cantilever, okay. But please remember, for a cantilever beam having a flexure member in continuation, the anchorage length to be provided is 1.5 times the span of the cantilever. If you are having a beam in continuation with this cantilever beam, and if you are anchoring this bar in the continuing beam, then please remember, if this is the span L, okay, then the anchorage length over here from this face of the column should be 1.5 times the L at least. Please remember that, okay. The criteria in this case will change, okay, okay. Now check for the deflection at the free edge. So maximum steel provided, the support is 942, PT found is 0.910, FS found is 212. So we'll take the next larger FS, that is 240, right? So we'll take the graph for Fs equal to 240, okay. Kt is found to be 1, this is 0.9, right? So when you take 0.9, and this is the graph we are referring, you get Kt is equal to 1, right? KT is equal to 1, KC we are taking as 1. So L by D allowable is L by D basic into KT into KC. For cantilever, L by D basic is 7, KT is 1, KC is 1, so this is 7. Now actual L by LD. In case of cantilever, fixed cantilever, court says the effective span for the cantilever to be taken is clear span of the cantilever plus the effective depth. Okay, so clear span is 1500, effective depth is 450, and divided by effective depth 450. So this is 4.33, which is less than 7. So it is safe in deflection. Okay. So this is how we do the design of a cantilever with varying depth, right? So I hope you must have found this video useful. Please visit website mmsprogramcivil.com for all the videos in PDF. Okay, they are uploaded over there. Thank you.